First of all, I will not talk about LLMs. This is a bit different process. I mean, no. I am an LLP AI developer, so I'm very passionate about that. But for this particular moment, I would like to talk about something different, which is OpenFL. How many of you are familiar with federated learning? Or how many of you have used something about federated learning? Okay, nice, cool audience. So before talking about federated learning, we need to introduce that you probably know, but most of the time when we need to increase the accuracy of our models, of course, we need more data. We need to increase the amount of data. And with LLMs, we are facing that you need even more data, right? But for other use cases, like can be, I don't know, with traditional machine learning, like fraud detection systems or recommendation systems, you need to increase the amount of data that you need, of course. But it's not just about increasing the amount of data that you need, because this data, it should be diverse. So even if you have a lot of data from one particular bank or from one particular hospital, you need to make it more diverse. So if you like to avoid the bias, for instance, as we can see, there are multiple studies or multiple publications. When you see, for instance, that healthcare AI systems can have a problem or can be biased for gender or for multiple things. Same happens with credit cards when you need a risk assessment system or when you need to provide a loan AI system. You would like to avoid the bias to those models, right? So we know that we need more data. We need this data to be diverse, but it may happen that this data it's not centralized in a place. Probably in some use cases, this data is in multiple sites. Could be multiple countries, multiple regions, or even it could not be easy as accessible. So the main problem is, it's not a problem, but when we would like to increase the accuracy of our model, we have some local regulations, right? We have IPA or GDPR, which means that if you have data, for instance, in Europe, that we would like to train a model in US or Canada or Latin America or whatever, you need to move this data from Europe to the place that you are doing or the place where you are training your model. This could be impossible in some places because if you have a regulation that the country is protecting this data, you cannot extract the data from the country to your model. So you may face a problem there. The other is because it's sensitive. Mainly in healthcare, where the data is related with patients, it's sensitive. So we are talking about the health of the people, and most health institutions, could be healthcare institutions, they don't want to share information because they don't want to share information of the patients. They will keep it private, of course, which I think that we can all agree that it could be not a good thing to share with our names and our history, our medical history. So we need to find a way to protect that. Or it's too valuable. Probably it could take years for a company to have a lot of data from customers or historic data, but they don't want to share that information to the competition, for instance. If you are working in multiple bankings, RBC, for instance, they don't like to share the data, identify it with Scotiabank. I don't know, it's just an example, right? But it's too valuable sometimes. And the other is the data silo problem. Even if you don't have this problem of regulations or is sensitive, if you are open to share the data, could happen that it's too large, the data to transmit from one country or to another country. So you have the data silo problem. So we need to find something to try to solve that. And I would like to highlight here that this is a tool, a framework that will go deep later, that is useful for this particular use case. If you are facing some use cases that is similar to that problem, you have a tool to solve that. If you have the 100% of the data, you don't have to be worried about that because we already have the data. Let's suppose that you have the 100% of the data. It's not the main solution for that. But in multiple cases, it can be very useful. So what is basically federated learning is when we talk about training models, you are probably, when you are training your models, they are being trained in a centralized way. So you have the data sets, you probably do some SQL queries, you download the data, you have it in a centralized way, and you centralize it in one device. Could be in the cloud, could be parallel training or whatever, but the approach, it's centralized. Federated learning enables, for instance, the models to be trained in a distributed way. So instead of having a centralized place to train this model, you can have this model distributed from these particular countries, for instance. But it has one more thing that is the key here is the privacy and the security. Because if you need to be moving the model, for instance, from one country or to another country, the main point here is the security or the privacy of this data or this model. You may probably know what is parallel training. Well, this is different because parallel training is focused on performance. So you have your cluster, your data center, you train your model in a distributed way, but it's always in your same cluster. Federated learning, it's different because you need to be aware about the security between the nodes and the centralized points, for instance. So security is the mainly concern when we are talking about federated learning. How we can work, or how we usually work in machine learning, it's the data. What we used to say is that the data goes to the model. So you download the data, you have institution 1, 2, or 3, for instance. That can be banks, healthcare, or whatever. You download the data, and you put the data in a centralized place, and you train your model, right? With federated learning, you have the data in each particular institution, and the data keeps in that institution. I mean, it's still present in that institution, and the only thing that moves from the institutions and a centralized place is the model. So you train the model in each particular institution, you send the weights or the updated model to a centralized server, which is called aggregator server. The server collects all these different models, makes weighted average. I mean, it could be something different, but it has a new version of the model. After the epoch 1, for instance, it has a new version of the model, and this version of the model goes to all the other institutions, and they do the second round of the training. And this is an iterative process that can help to update your model or to train a model in a different way. If you see, the only thing that is traveling between the institutions and the aggregation server is the model. So we need to find a way to secure how this weight or this model is traveling between institution 1, 2, or 3 and the aggregation server. To put it as an example, we as Intel, we work with the School of Medicine of University of Pennsylvania because they used to do some research about healthcare. And as it says, we run the world's largest healthcare federation. They wanted to train a model to detect tumor cancer, or yes, to detect tumors. And to do that, as a university, they talked to multiple institutions around the world, which was 71 sites across 6 countries, Latin America, Africa, Asia, Europe, I mean, tons of data. And they have, of course, the centralized place is the black point, where, as you can see there, that is in Pennsylvania. And they started to do the process. They started to train the model to see what happens in both sides, right? Because the first side was to see if federated learning really helps as a technique. And the second way will be to see how we can secure the data, or how the data is not moved between others. So how you can secure the machine learning model between one side and another side. The results that we have, we as Intel, of course, I didn't do it, but Intel, University of Pennsylvania, is that we increase the accuracy in a 33% when we compare with the local validation data. If you see, the blue is what was the public initial model, which was before training this model in a federated way. And the second one is how they train it after training the model with a federated way. So the model was trained with data from around the globe. And this model, it's compared with, okay, how this model performs with local data in each particular site. And it has an improvement on accuracy, of course, because if you train with your own data, the accuracy will be lower compared with the full data, right? The second one is something similar, but with out of sample data. It means with unseen data. So it also improved the accuracy of that. The main point here is that you are improving your accuracy, but because you are adding data that it's more diverse or it's not the same as the data that you can have locally. Sometimes it can be easy to find ways to talk to other institutions or to other banks to agree on that. But I mean, it will be a benefit for all the companies in that particular place because it's healthcare. So this model now it's improved something on the health for people. So the previous model has a lower accuracy compared with the newest one. So it was a healthcare a benefit for the health, we can say, right? The good results is something what I've been talking about is the increased data, of course, can improve the performance. However, data size alone cannot guarantee positive results. As we said, even if you have the data in one point, if you have tons of data in one place, it always will be good to have more data, right? Large sites, I mean, it's a bit repetitive of that. How we can run that? There is a framework that is OpenFL. It was initially developed by Intel and the University of Pennsylvania. It was developed by Intel Labs, which is a part of research that Intel has. And the good news is that now it's part of the Linux Foundation project. So it's part of the incubation. Intel donated the project to the Linux Foundation. So what it means is that all the decisions that should be taken in the project will be part of the community. It's not Intel deciding for the project, it's the community. So this is a very important point, and it was recently done. What is the difference between OpenFL and several federated learning frameworks? There are multiple federated learning frameworks. The reality is that OpenFL was initially built around security. So TLS implementation, for instance, is embedded. So you don't have to add any different configuration if you like to secure your environment. So it's enabled. This is the main difference if we need to mention a difference. And of course, it's pretty easy to use if you like to be involved in that. It's pretty easy, bunch of tutorials, bunch of examples. As I said, OpenFL is like a framework, but you need to train a model. When you're training a model in your institutions, you probably will be using a framework. Right? Framework could be PyTorch, TensorFlow, or Keras. So it's agnostic. This is the good thing, because if you are developing something in PyTorch, for instance, you don't want to change your framework. You don't want to migrate your framework to PyTorch to TensorFlow. The good thing is that you can use in both of them. There's a GitHub, there is a Docker version that you can download as a container, and to use it is as simple as pip install OpenFL. One of the problems when you are working with federated learning with the vanilla version, just to mention a few, we can have multiple types of attacks to federated learning. The most common is, as I said at the beginning, that the models are traveling from institution 1 to the aggregation server, to the server. An attack could be, for instance, if they poison the weights. So there is a way that someone could attack the weights, can see how the weights are updated, and they could access to the initial data just looking to the weights. So this is something that if you're not secure in your secure environment, of course, your federated learning process, it could happen. The second important one is the model IP theft. As I said, the model is present. It's a very cool animation. The model is present in all the institutions. So you have the model that you are training. It's present at the same time in all the institutions. So you need to really be sure that if someone, for instance, steals a model from one site, is stealing the overall model. So you need to be aware of that when you are working with that. The way to secure OpenFL counts with lots of mechanisms, with security mechanisms, like I said, with TLS and so on. But there is also one additional that is an add-on. If you probably heard about confidential computing, I don't want to go in detail because it could take hours to explain that, but basically it's when you are transferring data from point A to point B, you are protecting the data, what we call in transit, right? With TLS, HTTPS, and so on. But there is a point that when the data is being processed by the application, in the moment that it's processed, it's not secure. Because it's an extra layer, of course, it's a mitigation of that. But what confidential computing does is it makes an enclave between the hardware, could be Intel, could be NVIDIA, could be whatever, and the application. So the only thing that could access to this particular part of the code is the application that is validated by the hardware. It's a bit a hardware conversation, of course, I don't want to go there, but there is an extra layer of security. If you have probably heard about confidential computing, this is the extra layer. So basically what it is it protects the data in each point, it protects the data when it's transmitted, and it protects the data when it's processed in the institution, right? So let's suppose you have a model, you are training a MNIST model, and it's trained in a device. Could be edge device, could be CPU, could be NVIDIA, could be whatever. And you need to secure in this particular moment how to process the data. And this is an extra layer of security. How you can use it? Basically, this is the architecture. So you have a central point that is the aggregator, which is, as I said, which is collecting all the other institutions or nodes, let's call it nodes. And every node is training their own model, and they have to send the model to the aggregator, and the aggregator decides how to update the weights. But there is always a centralized point. And so how it works, you have something that's called the plan. When it goes, this is the model, this is how you'll be training your model, this is what will be the epochs, and so on. And you need a plan for that. This plan is distributed to each particular node. And the important thing, as I said, is you have the security part, which is a CA, you need to have a CA, you need to have a TLS. The good thing is that if you're not so familiar with security, or if you don't want to go in these details of security, OpenFL has already a vanilla configuration of CA, so you can download it, has a CA ready for you if you would like to use it. Of course, most customers would like to use their own CA, their own certificates, but there is something that people can use it if they want. People that is using OpenFL, as I said, University of Pennsylvania, VMware has also, they did some compression pipeline when you are training a model and you need to move the model from one side to another side. It could be heavy to transport. The reality is that it's very light, but sometimes it could be huge. if you are training an LLM, for instance, but no, just joking. They added a compression pipeline on that, and multiple others. And I would like to finish with a use case that I found really cool, that is the NASA. As I said at the beginning, there is the data silo problem, right? So even if you have the data, even if you don't have the GDPR problems, you need to move the data from one side to another side. And we probably think, okay, we have internet, we have access, we have connections, so how hard it could be to move the data from one side to another side? Well, for the NASA, when you have astronauts in Mars, and you would like to move all the astronauts' data to the NASA here in US, there is a problem. So they had to detect something about the radiation contamination for astronauts, and they have all the astronauts' information. And what they did is they used OpenFL, and they trained the model in Mars or in whatever the astronaut is, and they trained the model there instead of moving the data from there. Yeah, it's pretty cool. It's funny. But this is how you see, because you don't imagine when you are working with that, what is the problem that I can have with data silo? But when you have a Mars, you probably start facing that. Call to action: if you are working with projects with Federated Learning, or even if you are working on, if you are not working with Federated Learning and you would like to be involved, it's a project, it's an open source project, so there is people solving issues. We really appreciate if people would like to solve issues, to to provide features, and try out tutorials. If you'd like to start working on that, we have some tutorials. Blog posts explaining, even if you like to write a blog post, will be very useful. Documentation, we have our virtual community meetings every month. Yes, one in Europe and one in Latin America and North America. It's an open source project. This is the mind that we have here, so we are more than open to accept people to contribute and to be part of the project. And that's it. Thank you so much. I think that we have some time. We have some time for questions. Yeah. I can go there.
How do you deal with data interoperability when, especially for example, Pennsylvania has used for healthcare, and we all know healthcare is broken in all of these heterogeneous hardware generating different data in different format. How would Federated Learning deal with interoperability issues of different data provider, even different brands or different versions of the data that is coming?
Yeah, there is, thank you for the question. And there are some mechanisms that are aggregated. There are privacy meter, for instance, a privacy meter, if you like to test how validate or how true is the data that you are training in each particular site, right? There are a lot of features. But one of the features, it's about that. It's about how you can ensure that the data that you are using in your site wasn't corrupted or wasn't moved or wasn't modified.
The same structure is a matter, right? So on one version of a machine, you have integer value, for example. On the other one, you have float. So how do you deal with that?
Well, it's the same. It's the same, because when you are training a model, what you are doing is you have one model and one configuration. Instead of working the same configuration in one site, you have the same configuration in multiple sites. So if you are training with BF16 or whatever, or if you are doing quantization in a model, you have to do it for all the data, because it's the same process. So what you do when you have this part of the plan, it's you define how is the model trained, right? But could happen, for instance, that for particular hardware, the instructions underneath can be different, because you are using NVIDIA hardware and you're using Intel hardware, and the instructions are different. This it's not a part yet because we need to create an add-on, for instance, an add-on for a particular hardware to the application. We have that done just for Intel because it's an Intel project. Yeah, but this is the main, I mean, it's an idea. Yeah.
Ezekiel, I have a quick question for you. Great talk, by the way. Can this framework be deployed on ARM architectures?
It can. Yes, you can do it. The only thing that you don't have is the confidential computing part, because the part of the top is transparent. You can use any hardware you need. Our idea initially was to let that open to all the providers. So if someone would like to develop the add-on to ARM, to OpenFL, it's totally open to do it, and the same for NVIDIA. But answering to your question, you can use it, but not with this confidential computing part, of course.
All right, thanks.
So in terms of the acceleration part, I assume that the confidential part is basically accelerated on CPU and GPU, right? So can you actually explain in terms of the workload cost, right? When you do this confidential computing and then you accelerate, how fast you can basically do these things and that sort of thing?
Great question. And this is just the Intel part, the acceleration part. SGX is not acceleration. SGX is just encryption. Yes, you can think as encryption and decryption between application and CPU. This is one part, but accelerator, for instance, when you are defining this plan, you can use an accelerated toolkit of PyTorch, for instance. Intel has some extensions that can accelerate that. And when you are defining your plan, you can use the accelerated version of PyTorch of the particular library. And you will use both, right? So you use the accelerator part and you will use the encryption part. So it's totally open. This is why when you define a plan, it's the same as you can do in your computer, right? The only technical difference is when you are training a model with PyTorch, for instance, when you are doing the training, you are invoking or you are calling a training class or the class that PyTorch has to train the model, right? When you have NNN module and so on. What OpenFL does is this NNN module function is different because in the middle we need to say, okay, when you are training a model, instead of doing a new epoch, wait for an instruction, which is the aggregator instruction. Or when you are defining that, okay, these instructions will be part of the plan. So you need to look at the plan instead of the regular class that you can have in NNN module, for instance. Yeah, this is why you can use whatever accelerator you are using, you can use it. Thank you.
I think we've run out of time for questions. So if you have more questions, you can meet Ezekiel at the back after the talk. Thank you so much, Ezekiel, for the work.
Thank you so much. Thank you.